Eng Phys 2P04, Lecture 26, Moments from Internal Strain Sources. Let's suppose that you take two pieces of metal and you bond them together like we looked at in the last lecture, but now if they have different thermal expansion coefficients, then when you heat them up, they're going to try to expand differently. So let's suppose the bottom one tries to expand a little bit more than the top one does. What's going to happen is the beam is going to bend. How it bends depends on the ratio of the thicknesses, the ratio of the Young's moduli, and the difference in the strain in each layer. One way to calculate this is with the 1925 Timoshenko formula, presented here, where m is the ratio of the thicknesses, top layer thickness divided by bottom layer thickness, and n is their ratio of Young's moduli. Strains that would show up in the layers, if they were free, are epsilon in the one direction 2, and epsilon in the one direction 1. So this means the bottom strain minus the top strain, meaning that if the bottom was going to strain more than the top, you would have a positive radius of curvature, it would bend up. And if the top was going to strain more than the bottom, then this would be negative, meaning that it bends down. So if we substitute in the temperature difference with small t's here, T minus T0, and the thermal expansion coefficients, we can simplify this as follows. And it's not specific to thermal expansion, even though that's the way that Timoshenko analyzed it. You can also use piezoelectricity to get the same kind of strains. Now we'd have coupling coefficients times electric fields. Or if you substitute in electric fields for the voltage divided by the thickness of each layer, then you can write the curvature in terms of just voltages. So if we have two active layers, like the top layer and bottom layer are both piezoelectric, then this is, there's a name for this kind of actuator that's called a bimorph actuator, two active layers in the shape change, bi for two and morph for shape change, bimorph actuator. If you have only one active layer, so maybe the top layer is piezoelectric and then the bottom layer is not trying to strain, then it simplifies to this kind of a formula, and it's called a unimorph actuator. Let's look at this coefficient here, which I'm going to call the Timoshenko curvature coefficient. All this dimensionless thing based on the ratio of the Young's moduli n and the ratio of the thicknesses m. The maximum value of this coefficient is 1/4. By plotting the log of n versus the log of m, you can see exactly where that shows up and how they relate to each other. So if the top layer is much stiffer than the bottom layer, for instance, meaning that we've got a large n, so we're somewhere up here, then you want the bottom layer to be thicker than the top layer to give you the most curvature. So the optimum kind of actuators would have an appropriate ratio between the stiffnesses and the thickness. All right, so where did this Timoshenko formula come from? We can use the same derivation that we used last time, where we write the stress in terms of the strain, but this time differentiating between mechanical strain and physical strain. Physical strain being the relative length change, now writing it in terms of the neutral axis there, displacement, so position relative to the neutral axis, divided by the bending that results, the radius of curvature of the bending that results would be the strain at each point inside the beam. And so the mechanical strain is this minus the thermal strain, or maybe minus the piezoelectric strain if this is a piezoelectric actuator, or maybe minus both if we've got the general case. So then the moment is the integral of negative this, so the moment about the neutral axis for a cross-section, and substituting everything in, recognizing the definition of flexural rigidity in there, we've got this formula. Now if we don't apply any external moment to the beam, then the moment has to be 0, so you can solve this for 1/ρ and find that it goes like -1/EI, integral of E times position relative to the neutral axis multiplied by the thermal strain in that layer, integrated with respect to area. You can check whether this reproduces the Timoshenko formula with the example we're about to do. We're going to need some thermal expansion coefficients for metals. So here we return to the bimetallic strip that we solved for the flexural rigidity of last time. Instead of applying a moment to it, we're just going to apply a temperature difference. And because it was tungsten and aluminum, you can see now why I picked those metals last time, because aluminum and tungsten have a pretty different thermal expansion coefficients, so we should be able to get some good curvature out of this by heating it up a bit. Let's see how that works. Substituting in everything and using the same calculations that we had last time for the first part of it, where we calculate flexural rigidity and all that. Now, substituting into our Timoshenko curvature coefficient, we've actually got pretty close to ideal in terms of what we could have for that. So the aluminum is a fair bit more compliant than the tungsten is, and that's why the optimum thickness ends up being with having the aluminum quite a lot thicker than the tungsten was. So we want that to be thicker than the tungsten because aluminum is more compliant. Then we're going to get the maximum amount of curvature of 0.25 for our Timoshenko curvature coefficient. Substituting into all of that with the curvature coefficient here symbolized by gamma. Gamma is a good symbol for coefficients. We've got 6, the strain difference, which is just the alpha difference multiplied by the temperature change. And we end up with negative 0.148 per meter. Now, the check is, do we get the same result from the derivation that we had above? Substituting in the Young's modulus and thermal expansion coefficient as piecewise functions. Sure enough, yes, exact same curvature. So how much of a bending angle does this curvature lead to for the 30 centimeter long strip? About 2.54 degrees, and that means a 6.65 millimeter deformation at the end. So compared to the deformation numbers that we saw for reasonable loading, for most loading numbers, this is a pretty decent deformation. So this is a common sensor. By taking two metals with different thermal expansion coefficients and wrapping them up in a long coil, you can make a temperature sensor. This is how old thermostats are made. Basically, you would twist the dial to set the point where you want the thermostat to turn on. That kind of coils and uncoils a spring, and then as the temperature changes, it deflects this coil because the coil is made of two different metals in a strip. So that moves one end of it, and when it hits the when it moves because of the temperature change, then it creates a circuit. It makes electrical contact to some other plate of metal, and that will turn on or off your heater depending on whether the temperature is too low or too high. Another example, Pzt Bending Actuator. We're returning to the same actuator that we had before. These are the same dimensions, where we had a 5 centimeter by 1 centimeter by 1 millimeter PZT slab, except this time we're going to imagine that the bottom half of the PZT is pulled differently, so that the crystal Z direction for the top half is up, the crystal Z direction for the bottom half is up like it was before, but the top half crystal Z direction is down, meaning that we see effectively different electric fields and different strains resulting in each of the different sections. So in the bottom half, we end up with an X strain given by 17.1 microns per meter, but in the top half, we get negative 17.1 microns per meter. You could physically pull the piezoelectric crystal differently by growing one piezoelectric crystal and then cutting it, flipping it around, and bonding it back to the other piece like this. So calculate the curvature of the actuator and approximate the tip displacement if PZT has a Young's modulus in the x direction of 61 gigapascals. Okay, using, say, the Timoshenko formula, or you could do the integral way, we come up with a tip displacement of 64.1 microns, and this is quite a lot larger than the elongation of this actuator before we pulled it differently. Same dimension, same voltage. We got an elongation of only 855 nanometers. So flexion and these kind of bending methods are ways to get large deformations for actuators. Finally, let's do the FlexPDE example. So FlexPDE we can use to solve these problems if we set up different layers in FlexPDE, and that's kind of a complicated thing to do. So I'll give you a complete worked example. This is the aluminum tungsten bimetal strip, and we're solving it in FlexPDE. You've done a little bit of this in the tutorial, and you'll do a little bit more this week. So how this works is you are going to set up different values for these parameters in different layers. So first you declare them in the definition section so that you can use them in your equations here, but you don't actually set values for them. Instead, you set those values in the different regions. So this is a bit simpler of a region definition problem than the one that we did back in the start of thermal expansion, where we had the two rods kind of hitting each other. This one, we've got one plate bonded to another one, so we're going to set the tungsten as being a rectangle that goes in the downward direction, and then aluminum goes in the upward direction, so it's the top part of this beam. Plotting all of that, we get the following deformation, which matches the tip displacement that we were predicting. Okay, and one last comment, multimorph curvature. So in reality, piezoelectric stack actuators are rarely true unimorphs or bimorphs, where we just have two layers, one of which or both of which may be active, because the electrical contacts have some thickness and they can affect how the material behaves. So for that reason, or in general, you may be interested in analyzing an arbitrary number of layers, and while the Timoshenko formula doesn't extend to that very well, the calculation that we did involving an integral does. You could even have a continuously varying Young's modulus along the length, continuously varying piezo or thermal strain along the length. And in fact, you don't even necessarily have to set the moment equal to 0. You could analyze it in response to additional moments as well to find out the total deformation. Great.